So the next section here in abstract algebra is about functional programming. And I want to go through a little bit of history, rolling the clock back to the 1930s. So what's that, 80 years ago or so. There were a couple of people who were really important in the field of functional programming. At the time, of course, there wasn't a whole lot of programming going on, but they established a lot of the math that became quite useful for this. The first one is Haskell Curry. Haskell Curry, actually see his name showing up. There's the currying that people talk about inside of functional programming. They also have a functional programming language called Haskell. Haskell Curry had done a lot of work on combinatory logic. And that shows up in what we do. I'm not going to go into a lot of details of it, but along with that, there was Alonzo Church, probably even better known, who had worked on something called lambda calculus. Curry's work was in 1927. Church was in 1936. The bottom line is that they were both struggling with formal answers to the question, what could be computed? What could be calculable? And the reason why I'm calling these out is that, not so many years later, digital computers were beginning to be built, and people were grappling with the real aspects of programming. What can you do with a programming language? What can be computed? So if you look at Alan Turing and other people who, not many years later, were working on computers, they were making reference back to the work from Haskell Curry and Alonzo Church. Lambda calculus, of course, shows up in a lot of places. Now, rolling the clock up, let's see, that was the 1930s, and then we got through computers in the 1940s and 50s. Rolling the clock out into 1970s, there was ACM is an organization called the Association of Computing Machinery, if I've got that right. ACM is a very famous organization in CS. And there's the big award they present. It's called the Turing Award. In 1977, the Turing Award was presented to John Bacchus. And it was regarding a paper that he had done entitled, Can Programming Be Liberated from the von Neumann Style, a Functional Style and Its Algebra of Programs? So the idea is that John Bacchus, working at IBM, wanted to try to understand how could you make programs that you could split into little parts and run in parallel. How could you increase the parallel processing? Essentially, how could you run things on clusters? Back then, they had mainframes, not as many clusters. I will admit to having written programs back in that era, and they were on mainframes. Fortunately, we graduated into Apple IIs not too many years later. The interesting thing about John Bacchus is he also led the team that created Fortran. So back in the day, one of the earliest programming languages, formal programming languages, was Fortran. Of course, so many things have been written in Fortran over the years, and Bacchus led that effort. He really understood what it meant to build a compiler, because his team had to struggle with building, one of the first really good compiler efforts. And von Neumann is the other thing we're mentioning here. That references back to John von Neumann, who articulated a lot of the math that goes into our ideas of what can be computed. And there is what's known as von Neumann architecture, refers to having a CPU and having RAM and having buses and things like this. Typical style of computers. And the problem with the typical style of computers is that it's hard to make things parallel. So, make a long story short, John Bacchus wanted to understand how to build clusters, how to build compilers that could take advantage of clusters. And he used lambda calculus, again from Alonzo Church a few decades earlier, to come up with the definition of what he called a functional programming language, FP for functional programming. If you read the paper, it's actually, I find it to be pretty accessible. It's interesting, though, because he really does talk about abstract algebra. So, going back to the 1970s, the premier computer scientists were thinking about how could we leverage abstract algebra to build compilers that would work with clusters much better. So there's a couple of points in the paper I'll bring out. One was the functional programming algebra is compared with algebras associated with the classical applicative systems of Church and Curry. So going back to lambda calculus, but making reference to abstract algebra. And a little bit later in the paper, he's talking about programs can be analyzed and optimized by an algebra of programs. Since the state cannot change during the computation of a given system X, there are no side effects. Thus, independent applications can be evaluated in parallel. So let me cut over to some Lego blocks. Again, my daughters were kind enough to loan me some Lego blocks to roll with here. The idea is, going back to semigroups and monoids and all that, we were talking about code reuse. And the objective there is to come up with different blocks that can be reused, essentially assembling them together in different ways, different shapes, to build different types of programs. The idea is that by leveraging the abstract algebra, by having the right properties defined for your code, then we can start to use abstract algebra to compute about the program itself. How can we analyze and optimize by an algebra of programs, as John Bacchus called it? And that's where functional programming really came from. The idea was you could have essentially a pipeline of data, functional composition, and you don't have a lot of side effects, so the compiler can really track what's going on and maybe move parts of code from one part of the program to another to make it more parallel or make it more efficient. But again, it's all based off of being able to leverage building blocks. So if you were to translate John Bacchus's paper, it's a lot about Lego blocks. Now there's 4 key elements of functional programming that Bacchus cited. One was a functional style of programming without variables. Again, this is very different than Fortran, which his team had built, which has a lot of variables. Number 2, an algebra of functional programs. Number 3, a formal functional programming system, that is, say, a compiler that can compile this code. And then number 4, an applicative state transition system. It's a big fancy word for some concerns in software engineering where you want to be very careful about the side effects and how much state you're introducing. We'll go into some of that later. Anyway, this is all really good stuff. It's a great paper. It's straight to the point. And it's well worth a careful read. But the language that was described, this language FP, wasn't really useful in practice. It was more of a academic theoretical exercise. So, if you go on GitHub, you're not going to find many open source projects that are based in FP. But it definitely set the stage for what we would look towards in the future for functional languages. Okay, that was in the 70s. Rolling the clock up a decade and change later, a lot of different research efforts which were looking at functional programming, things coming out of Lisp and whatnot. A lot of these efforts converged into an open standard that was called Haskell. Haskell's named after Haskell Curry, and it really put into practice much of what John Bacchus had envisioned for parallel processing. One of the things about Haskell is that it's a very strongly typed language. And the types are interesting because they implement certain things out of abstract algebra, certain kinds of abstractions, like monoids. And they allow you to perform certain operations, maps and folds. Essentially, they provide a kind of MapReduce framework. So if you've heard about Hadoop and MapReduce, a lot of the ideas came from back here. The long and short of that is that you want to take some of these abstract algebra notions, some of these building blocks in Legos, per se, you want to apply those to work on very large types of data structures, whether those be graphs or trees or matrices or whatever, but you want to apply those at scale, do a lot of parallel processing on big data. And that's where Haskell was leading. This is in 1990, and we didn't really have a lot of open source frameworks for clusters back then. That wouldn't come around for another decade or so. But the ideas were being built out. There is a really excellent book, I find. It's called Learn You a Haskell for Great Good. It's by Miran Lipovaca, and I highly recommend this. In particular, there's an excellent chapter on monoids, functors, and applicatives that goes into gory detail about how you could use a functional programming language to implement these notions out of abstract algebra. The type system in Haskell is where the abstract algebra shows up most directly. For example, in the Lipovaca book, where they talk about monoids, they compare them, they say that they're sort of like socks. You can take some chunk of code and wrap it up in a way, like putting a sock on it, basically. Wrap it up in a way that you can kind of think of how these Lego blocks have little connectors on them. So how do you define the connectors so they can snap together? That's the big idea. And with monoids, the definition in Haskell is that the function takes two parameters, so it's a binary operation, and the parameters and the return value have the same type. That is to say, there is closure within the set of that monoid. And also, there exists a value that doesn't change other values when used with the binary function. So there's an identity element. If we're talking about elements such as natural numbers, and we're talking about an operation such as addition, then the identity element would be 0. Add any number to 0, you get the same number back. That provides, well, yeah, that's identity element. So you've got those three aspects there of monoids that are implemented, and again, it's because of this type system. So, computational thinking alert. We can take graphs, and we can represent them as, say, trees or sparse matrices. And frankly, a lot of real-world problems end up, a lot of data problems end up being represented as graphs. And then we can take monoids to define robust mathematical definitions for how to compute portions of some large set of data, but compute it in chunks. And in particular, we can have very formal definitions for how to handle the empty elements. So if you've got a big graph or a sparse matrix, you know how to handle the empty parts very quickly. In fact, you can just slam them all together because of the mathematical properties. So we could say then that the notion of graphs and monoids, sparse matrices, it all fits together really well in the sense of computing with very, very large sparse data sets. Now, in terms of computational thinking, this is interesting. When we talk about designing algorithms, monoids allow for efficient partitioning of the data and also essentially cutting up the computational tasks to send it out across a cluster. The takeaway is then we can split a wide range of computing programs, whether they be graphs or matrices or whatever. We can split those up into little chunks and compute them out across the cluster and then reassemble them back together. So we can do our work in parallel, again, taking the different building blocks and running these in parallel through some kind of cluster. Let me build up a little pipeline here. And we have some guarantees that when we get to the end of the pipeline, we'll be able to take all the chunks and reassemble them together efficiently. That's what we're trying to do with the monoids. In terms of algorithms, what's interesting here is that when you have a really large data set, say you have a social graph that has 100 million different customers in it, you probably aren't going to be able to fit that all on one computer. By definition, you're probably going to have to split that up into a number of different servers. How you split that up is very crucial to how you solve the problem. So if you have some guarantees, by virtue of, again, using the abstract algebra, that you can cut things up into chunks very efficiently but still assemble the results back together in parallel, then you can handle a really large data set on a lot of computers. That's the big idea. Now, rolling the clock out to 2007. This was shortly after the open source framework Apache Hadoop was introduced. It was a little over a year later. There was a Java API called Cascading. It was written, the author is Chris Wenzel, and he introduced this, I think it was November of 2007. But the idea was being able to build enterprise data workflows on top of cascading. So, I was talking earlier about data workflows, and I was talking about functional programming. Pulling all those pieces together, Chris Wenzel's idea was that rather than writing code directly in MapReduce, which is kind of difficult, I've hired a lot of people to do that. I've led teams doing that. It's hard to find people who can think in MapReduce. But instead, what Chris Wenzel's big idea was to take some aspects of functional programming and make them available inside of Java with this new API so that Java developers could build data workflows, big data pipelines. And then down at the bottom there in this graph, we're showing a kind of data pipeline. I think this is a kind of word count. But essentially, there's a lot of building blocks in there. And again, snapping the pieces together. You might have one piece that reads in a piece of data from your log files and another one that reads in a piece of data from your customer profiles, and maybe we'll snap them together by having, I don't know, some kind of a filter, and maybe we'll do a group by, and who knows, maybe there's some errors that we want to trap. So we're going to trap those errors and send them off to our customer support people to read, and then all the results get sent out to some report that's put in a dashboard, some kind of pipeline. But again, this was interesting because it introduced functional programming into Java, not particularly a functional programming language. It provided that kind of abstraction layer. So we talk about separation of concerns. We talk about thinking of your business logic up here and then the implementation details down below that the compiler handles, and you have kind of a barrier or separation in between. So what cascading was doing was to borrow these notions out of Haskell's type classes, functors, applicatives, monoids, etc., and represent those as building blocks, patterns, like you would do with Lego blocks, so that people could build pipelines, and then just let the compiler handle all the details of all the minutiae of Hadoop implementation underneath. Now, one thing about cascading is that the functional aspects of it were very much used, and that came into a lot of interesting compiler theory and query optimization theory, but they weren't really called out. So when people were programming with cascading, they were thinking of doing patterns, pattern language, all these building blocks, but they weren't connecting the dots to say, oh, that's a monoid. Now, pulling in a concept we talked about earlier was composition of functions. You could have y equals f of x and v equals g of y. So you can take, from the earlier example out of the Algebra 2 refresher, we can take and compose those functions, apply one to the other, and come up with this composite. That's how people build pipelines in a functional programming language for big data. Cascading makes a lot of use of that, and that's one of the things that really defined. Now, a key takeaway is to ask, what's the data look like when it's flowing through those different steps in the pipeline? When data comes out from different sources and moves through the pipeline, what are the intermediate pieces looking like? And the idea there is you can let the compiler handle that part. So there's schema for your data is well defined at any stage. And the intermediate values, the data flowing through there, are shaped in ways kind of like how the connectors on these Lego blocks allow them to fit together. And that's an interesting point, because usually when we're talking about big data, we're talking about unstructured data, and schema may not be something that we have immediately. So this notion of applying functional programming was a way of really defining, letting the business logic define what the schema of your data is. That's an important point. We'll come back to it. But it's essentially, it's a computable schema. We talked about code as data, being able to compute about the code to be able to make it more parallel. Okay, now this comes into this term monoid that I've used a lot. Its contemporary usage traces back to Claude Chevalier, 1956. There's an interesting abstract algebra textbook where he introduced the term monoid as an internal law of composition. Actually, a related term is monads, and that really traces back into Greek philosophy. Definitely the Pythagoreans were discussing notions like that. That was very much revisited during the Renaissance. Giordano Bruno, John Dee had hieroglyphic monad, Leibniz, etc. They were really exploring a lot of these ideas and how they would apply in mathematics during the Renaissance. But the usage that we have traces back to like 1956. So there's a project called Scalding that Twitter introduced as open source in 2012. It's a Scala API on top of cascading. And the idea was Twitter wanted to rework their revenue apps based on Scalding, basically rebuild everything so it could run efficiently, leveraging the abstract algebra notions, but run on these huge clusters. So they came out with Scalding, and they've been evangelizing it, helping other companies to adopt it. So it's now used at scale by production deployments at eBay, LinkedIn, etc. And there's a link here. If you go to engineering.twitter.com under open source, there's a nice write-up about Scalding. There's great wiki on GitHub for the project. Excellent developer community around that. But it really pulls in a lot of these notions that we talked about out of Haskell on one side, builds them on top of cascading, and provides them in the context of Scala, which is a functional programming language, which is gaining a lot more adoption, especially for big data, throughout enterprise. I see a lot of deployments for them. Now, if you'd like to see some good books along these lines, Programming Scala by Dean Wampler, really excellent book if you want to jump into Scala. There's another one called Big Data by Nathan Mars and James Warren. It's due to be out this year, but there's an early access that's available online. And also a book specifically about cascading enterprise data workflows. I wrote that last year, also available here on O'Reilly. So let's pull this back into a kind of use case. We talked about the example company, foobartender.io. And having recently hired a new engineering director, she was coming into the problem and taking a look at what the company needed to do with this big data. And by reviewing what's available with functional programming and enterprise data workflows and some of these concepts out of abstract algebra being applied, she had some key takeaways. Number one, you've got this issue of interdisciplinary teams, data science teams being pretty much interdisciplinary by definition. But you can get them working together on building blocks, defining a lot of building blocks, like I have here in my Legos. Building blocks for the business logic of the applications that your team has to write. So one of the key takeaways was this a way of getting your team to work together more effectively. Number two, there's a lot of great off-the-shelf solutions that are available in Scala, Python, other functional programming languages, Clojure, I like a lot. In the .NET side of the world, there's F#, very popular language, some excellent abstractions in F#. Number three, there's an engineering problem of, you've got your team working on these large-scale clusters. They take a whole lot of time to troubleshoot things out on the cluster. It can take a huge amount of expense, really. And maintaining the code over time can also be problematic. So you want to minimize the complexity of the building blocks down here. You want to have very tight code, not a whole lot of lines of code. And you want to be able to reuse that code. So, one of the key takeaways is that by leveraging functional programming, you get really tight code. Often we see like a 10-to-1 reduction in code volume when you're comparing, say, a Java app or a SQL app versus, say, a Clojure app that does the same thing. And a 10-to-1 reduction in code volume has a lot of implications on how expensive that's going to be to maintain over time. Another thing, which is kind of subtle, but it was very interesting when I first encountered this. By virtue of having this separation of concerns, you have your business logic up here stated in a functional programming language, and you let the compiler implement the details. By virtue of having that, then you can switch out what the basis is. You can actually build out your business logic on a laptop and then compile it and run it off on the cluster. But you do your dev and your test, your cycle, there on your laptop in a local environment without burning all the time and money out on the cluster. And that really helps using this functional programming, especially using the abstract algebra. That's been one of the great lessons from Twitter. So speaking of that, there's excellent case studies out of Twitter, eBay, Etsy, LinkedIn, Climate Corp, Nokia. I could go on and on. But as far as using functional programming for big data, there's a lot of great open source from these companies, these projects, and a lot of great case studies to show what the business use is. And frankly, they're leveraging a lot of the abstract algebra concepts.